Hello, today I'd like to talk about classical keypoint localization technique. These are the class objectives today. We will talk about some of the related components so that you can find some paper from here. And then we will move on to talk about the locally invariant features. And we will actually talk about keypoint localization followed by this Harris corner detector. These materials are already covered in the chapter 2 of my draft. So if you're interested, you can go over. You can look over the draft for the detailed information. Also, as a review of the last lecture, we talked about these various student activities, including paper presentation, also this project presentation. Then we will talk about this grading policy. So before we talk about the today's lecture material, I'd like to talk about this basic homework for everyday class. I recommend you to review the lecture slides before you're watching the YouTube video. Just spend 5 minutes. That way you can also more effectively watch the YouTube video. And then I'd like to encourage you to come up with one question on what we have talked about today. You don't need to try to come up with the fancy questions. Just write down the question that naturally arrives to you. You need to write the question 3 times before the midterm exam. Then also I already identified some of the common questions in my draft, so you can see some of the questions. Of course, you can also use the ChatGPT. Also, you can ask if you want to know the answer of the answer to those questions, you can directly ask me at the class. So actually, up to today we will have this YouTube lecture, but from the next Monday we will have we'll get together on the class. So please come to the class next Monday. Basically, there are many papers related to this image search, also the matching, also the similarity, the techniques. So basically, you can try to find the paper from the computer vision conferences like CVPR, ICC, and so on. Also, there are many this machine learning the conference that also they're showing they also feature this image search paper, new RIFT, ICML, ICRL, and also there are many this computer graphics conference, also the multimedia. There are many related conferences, so depending on your interest, I recommend you to browse search this paper. Also, for the paper presentation, you need to actually present the paper that are published recently. So this is actually one of constraints. For the paper presentation, the paper should be published since 2020. And then again, you need to find the browse 2 papers, also video, and submit 2 summary before every beginning of the Monday class. So next Monday, if you come to the class, please browse 2 paper and submit the summary. Also, you can submit this summary at the online link that actually available at this course homepage. Also, think about the possible team member. So it may be too late if you think them later. So also next Monday, if you get together, we'll talk about the actual team member. Now let's talk about some of the materials of this image search. Again, image search actually nothing but a content-based image search. This is actually the identify similar image given a user-specified image or other types of input. But as a simple setting, we are just assume that user provides some sort of the input image, and then we need to actually search over in a very efficient way under the web scale image database and identify the kind of the similar looking or similar semantic meaning image to the user. To do that, actually, we typically extract some sort of descriptor instead of the RGB image. But actually, there are many important key components of this image search technique. First of all, we need to talk about image representation, and then we need to somehow store the available image at the DB, so that actually we can provide a very efficient searching from those a lot of images. Then also we need to have some sort of the matching technique So that actually we need to give we need to able to identify the similar image and provide those similar images to the user. Also, there could be many other these downstream tasks. We can also develop the classification, localization, and so on, depending on these components. So basically, the classical techniques or GIST or the recent deep learning, the convolutional neural net-based feature, they are mainly designed to invariant to the different transformation. We'll talk about what I meant by this different transformation. So basically, at high level, at pre-processing, basically there are lots of images, right? And then we build the database for the efficient retrieval at one time. But this pre-processing time, we collect those images and somehow extract the feature, and then we actually organize them into some sort of database. There are many different indexing schemes. Back then, actually, we use this vocabulary tree, but we can use the hashing of inverted files. But recent system actually we are using this some combination of this hashing technique or inverted files. We will talk about those techniques later on. And then at one time, actually, given a query image provided by user, then we actually go over those inverted files in an efficient way and then identify the similar images. That's the one-time process of the image search. And also there could be many different types of this post-processing. So given the query image, we typically provide some sort of this top K image. In this case, top 100 images. We call it this actually short list. So basically, if you actually type some of the text in the Google search, then Google search provides some of top image, right? Actually, this is called short list. And then in this case, given this query image, top one is actually very similar to each other, but other one is not that similar. But there are some of some another image, kind of late image in the short list appearing here, which also looks very similar to here. And then we can also do some sort of post-processing. So maybe typically we call this kind of post-processing as the re-ranking. Typically we are using the spatial verification, also known as the ransack. I will talk about those techniques later on. But the main idea is that by looking at the image more carefully as a post-processing, we can actually push this kind of similar images that are located late in the shortlist more this earlier position in the shortlist. That way, actually, user can more effectively find the similar image in the top rank in the shortlist. So let's get back to our this Bayesian image descriptor. So we know that actually RGB images themselves are not robust for the various chain. I mean, there could be many different chains. In the end, suppose that this is actually we are looking at this book in two different sides. In the ideal case, they look a little bit different each other, but somehow we actually convert them. We convert this image patch into the canonical space so that actually we can have we can actually have a very similar looking image patch. If we can do that, actually we can actually use the RGB the patch itself, but there could be many other the change. So instead of using the RGB image, we are using some sort of the image descriptor, and then these descriptors actually classified into the two types. One is the global feature, another one is local feature. Global feature typically encode the overall context of the image. On the other hand, we can also extract many of these local features that encode these different part of the object. Basically, the global local features actually complementing each other, also useful. But by now, we focus on the local feature for now, since we cannot extract we typically extract the local feature, many local features around this image. Then we can achieve more robust to the various change. So what kind of change I'm talking about here? So basically, here actually the same object looks different, mainly because that we are looking at the same object in a different viewpoint. So in the end, we want to have the robust image descriptor across these different viewpoint variations. Again, there could be many different illumination change. We can understand that they are looking at the similar scene, but we definitely need to come up with the images, some sort of the descriptor that actually the robust to this kind of illumination change, scale change. Also, sometimes actually we have this kind of deformation, but we need to be able to identify that they are similar objects. Also, there are occlusions. So, due to this occlusion, that's why actually we are focusing on extracting many local points. Also, there could be a lot of the background clutter. So everything looks very similar, but we need to be able to identify what are the actual foreground object, what are the background object. Also, even at the same class, in this case, the chair, there are lots of variation, intra-class variation. Still, we need to be able to understand them at the same class. So, if the user wants to extract some chair, we need to be able to identify we need to be able to classify them as a chair and then provide them into the user. So, as an example of the image search, is this image matching? This is actually I guess this is the Trevi fountain. In Korean, it's a 삼거리 분수대. So basically, here we can actually you can see that you can match this one to here, right? This is more easy setting. But actually, if you look at this one in a different viewpoint, in a different illumination, it looks a little bit different, right? In the end, it's the same thing. Also, we can talk about this as classical application of image search. This is not image stitching. To do the actual image stitching, we need to align them together. First of all, we need to be able to identify some sort of local feature. I mean, we can actually extract a lot of these feature points, and then we need to be able to identify what are the corresponding pair across these two different images. If we actually identify this peak to the peak and so on, then we can actually align them together like this. Then we can actually merge them. So this is actually called image stitching. So to do that, actually, these are some of the main component, and then also these are also we share this component with the image search. So how can we do that? First of all, we need to be able to detect the same point, even though without looking at the other part of image. So basically, we need to extract the feature only from this image, also only from this image, right? And then if we extract the feature like this, like them, and obviously we can actually match them. We cannot match them correctly. So basically, we need to, even though we are looking at only one image, single image, we need to be able to detect the same feature and again. For example, peak should be, if we actually extract the peak here, we also need to extract the peak here. So we definitely need some sort of repeatable detector. And then we need some other actually encoding some of surrounding the patch, and then based on that information, we need to also able to identify this corresponding the point. So in this case, we need to able to make this point to here, not the other ones, right? These are actually some common requirement for this image descriptors. So this kind of the problem has been studied a lot. There are lots of the technique along this classical approach. And again, they are manually designed in the image processing or the computer vision field. But as you know, recently actually we are also using more of this deep learning approach, which actually automatically constructed through this data. In this class, we first talk about this classical approach, and then we will move on to the deep learning approach. Even though this kind of classical approach kind of out of date, by looking at some of the classical approach, we can get some of intuition. So early on, there are many detectors like the Hessian, Harris, Laplacian, and so on. But actually, in the class, we will briefly talk about Harris corner detector. So again, the key point is also known as key point localization. This should be the repeatable. We need to be able to do the repeatable detection, precise localization, and then that point should be interesting point, right? And then all your approaches actually they're mainly look for this two-dimensional signal chain in the image space. So basically, there could be many different key point, but actually this Harris corner detector look at the actually corner. That's the reason why we are doing that. It turns out that actually corner actually they turn out to be repeatable and also very distinctive. So here, this actually the design criteria. Suppose that we actually will look at to detect the local feature. We look at some sort of the local window under this image, right? This actually local window, and then basically when you are looking at the images through the local window, we should be able to recognize the point by looking through this small window, the locality again. And then in this case, actually, when you're actually moving this window from that direction, in this region, this flat region, there's nothing changed, right? But on the edge case, if we actually moving this window along that chain, there could be a lot of change, but along that one, nothing changed, right? But if you look at the corner, basically whatever direction we are changing, actually there could be some sort of this content change, right? That's why because of this that kind of the property, basically the corner turn out to be actually very interesting, also this distinctive the key point. So how can you actually turn out this kind of intuition into some sort of mathematical formulation? So early on, we'll look at this kind of, this actually the very well-known Harris detector formulation. This is nothing but autocorrelation function. So basically, we are looking at the image I, the IXY against itself. So basically, that's actually we actually look at how the image itself actually the change. But here, basically, we look at we actually giving some sort of the shift as an amount of UV, and then we look at how the image actually content variation change. Also, the W is actually the W actually window function. We can typically use some sort of the Boolean function of Gaussian function. You can we can typically also we are using the Gaussian function. Also, by looking at the change, basically we are looking at what are the intensity change. So here actually through this window, we look at how the value actually changing. And then through this autocorrelation function, and then we actually this can be approximated into this kind of quadratic form. This autocorrelation function of E as a function of UV, another U and UV here, and then this the matrix M. And then this M actually known as this, in this case, at the case of the axis aligned corner case, in the simple cases, actually the M actually turn out to be there like this. The X and Y actually there's some point in the local window P. Here, basically IX is actually gradient along the X. IY is the gradient along the Y axis. And this actually scale of IX, scale of this IY, and basically this is also known as the second moment matrix. But at the case of this corner, this actually matrix turn out to be the very simple format like this: lambda 1, lambda 2, and 0 and 0. So basically, in this case, each lambda is corresponding to the image gradient along the X and Y. And then at the corner case, this lambda 1, lambda 2 becomes some big number. And also it turns out that this can be also extended to the rotate the corner. Here I didn't really talk about how this function derived to the up to here. If you're interested, you can actually go over the chapter 2 of my draft. But I don't want to talk about the low level details here, since I don't want to spend too much time on this kind of classical technique. Instead, I will move on to this recent deep learning. But it turns out that actually by looking at this value, if you look at this kind of edge case, in this case, if you look at the gradient along the X, in this case IX turn out to the 0, right? But IY become the very big, right? And then you can see that if you have the IX component, it will be 0, 0, 0, some sort of non-zero value, right? Edge case. But at the corner case, here, if you look at some sort of local window, it turns out that actually in some case, it turns out to be some of the within the window, some portion of IX, IY could be the 0, but along this at some of the case actually, some of the cases actually it actually non-zero, right? So that's why it actually non-zero value. It could be it actually turn out to some value very close to 0. So that's why actually we can have this kind of one. And so lambda 1, lambda 2 actually turn out to very big. It's the corner. if the sum of the lambda 2, maybe in this case lambda 1, one of the lambda 1, lambda 2 is very big, it means that, as I mentioned before, it could be the edge, right? So if either one of the lambda 1, lambda 2 is very big, it turns out to be the edge. If the of course, if you look at the flat area, you can see that actually all the gradients are 0. So then lambda 1, lambda 2 is actually could be the very 0. In this case, actually flat region. So based on this kind of the manual characterization, we can identify in what cases we can have the corner, right? And then we can actually develop some sort of response function R. In this case, the response function R can be we can design some sort of function, response function R, in a way that when lambda 1, lambda 2 are both of them are big, then we can, the response function can be big. So out of this input image, we are looking at the same object with a different viewpoint, also with a different illumination. This actually, the idea we talk about the exact definition of the response function, but when the response function is very big, in this case blue case, then we can actually identify key point is very small. It looks very small, but if we overlay the key point where the lambda 1, lambda 2 is very big, basically if you see that actually there are lots of these response point, corner point, but you can see that there are one corner. Here also another corner and corner. You can see that some of the identifier as extracted the key point, actually they are repeatable. Also they are actually extracted across the different viewpoint, and then this illumination change. Obviously it's not perfect, so in this case, for example, here we have this corner here, but in this case actually there are no matching point. So obviously there are some of the cases that are not matching each other, but out of extracted maybe the 100 corner, we wish that we can actually have maybe a big chunk of the matching point. So obviously recent technique, actually we are also improving the accuracy, the matching accuracy. But back then, this actual result of Harris corner detector, back then it was very good result. This is the result across in some of the input images. You can see that actually you can extract the corner point very well. Even if we apply the Harris corner detector in this case, actually we got this kind of result. Also, we apply this corner detector in this kind of stereo image, and based on that also we can do the actually finding the stereo correspondence, and then we can actually align them together. How about the rotation chain invariance? Actually, I didn't really talk about the details here. But actually, it turns out that actually, even though there are some sort of the rotation, we can actually have this kind of we can still utilize this kind of the form here. It looks a little bit for the rotated case, it looks a little bit complicated, but still we can actually have this kind of format. So the still same response function can be applied, but it gets more complicated. But how about the scale invariance? In these cases, actually, it turns out in this small window, it can be the corner. But if we're zooming in, for example, we actually we take the same photo with the zoomed in view, then the corner maybe looks like this. Then if we look at the same patch, with this kind of image patch, then everything maybe looks like the edgy, right? So it turns out that the basic Harris corner detector is not invariant to the image scale. So that's why there are another more advanced techniques that are robust to the rotation and other things, including this image scale. So these are actually some of the main material that I talked about. I briefly talked about some of the related conference so that you can find some of the paper along the course theme of the lecture. And then I wish that by now you can understand some of the locally invariant feature. And we talked about also the Harris corner detector, basically manually designed detector. Recently, obviously, we actually using the automatically learn the detector using the deep learning, which we will talk about later on. Okay, that's it. So the next time we will talk about the SIFT, which is alternative scale invariant region selection. Again, I recommend you to go over the next lecture slide before come to the class, and then come up with the one question on what you have talked about today. You can submit it through this online submission. Also, go over a recent paper on the image search and submit their summary before come to the next Monday class. So next Monday, please come to this class. See you on the class. Bye.